Hey guys, welcome. Yeah, so if I said I enjoyed making this video, then I'd have to be a true masochist. So I'm not gonna say that. Instead, I'm gonna say, "Sweet Lord Jesus, this was so much work," and even that's an understatement. So how do you repay me for my hard work? Well, if you believe in Jesus, that'd be amazing. That's enough payment for my hard work. But otherwise, until you get there, if you enjoy this video, that's a good start. Now, to start, notice that x to the 7th plus 1 can be factored as x plus 1 times this 6th degree polynomial. It's easy enough to see why x plus 1 has to be a factor of x to the 7th plus 1, and that's because we can easily see that x equals negative 1 is a 0 of x to the 7th plus 1, and so therefore x plus 1 has to be a factor. And then the other factor is a 6th degree polynomial. Now, this 6th degree polynomial has 6 complex zeros, and therefore x to the 7th plus 1 has 7 total distinct roots. One of them is x equals negative 1, and the other are 6 complex roots that come as conjugate pairs. Remember, complex roots come as conjugate pairs. And so we have a total of 3 complex conjugate pairs, and x equals negative 1 as being the 7 roots of x to the 7 plus 1. So we can write them x1 all the way through x7, and when we do, we're going to say that x equals negative 1 is x4. Now, if you need a little bit more help on figuring out the zeros of x to the 7 plus 1, then this might be the help you need. Note that trying to figure out where x to the 7 plus 1 is equal to 0 is like trying to figure out where x to the 7 is equal to negative 1. Now, all of the complex roots to this polynomial will have magnitude or norm equal to 1. So then to start, you can write x is equal to cosine theta plus I times sine theta, so write x in polar form, and then you need x to the 7th to equal negative 1, meaning you want cosine of odd multiples of pi. Now, if what I just said is not sufficient help, then you might need to watch a full video on De Moivre's theorem. I don't have a video on De Moivre's theorem yet, but it's to come soon, and yeah, so keep an eye out. But if I list all 7 roots, then you might be able to see what's going on. Actually, I'm not gonna list all 7, but I'll show you 5 of them. You've already talked about 1, and that's x equals negative 1, right? Okay, anyway, here's the first complex root. And x equals negative 1 is also a complex root, but as I said, we're going to list it as our 4th one, x4. Moreover, x equals negative 1 has no imaginary part, whereas x1 here does have an imaginary part, namely sine of pi over 7. And yeah, so for this x1, notice that x1 to the 7th is negative 1. That's what we need, right? Because then x1 to the 7th being negative 1 means this is negative 1 plus 1 is equal to 0. Therefore, x1 is a root of x to the 7th plus 1. Alright, and then our second root is going to look like this. And then our third root I'm going to leave out in the interest of space. So our 4th root, which is equal to negative 1, as we said, comes from this factor, x plus 1, right? And that's this. You can check that x4 is equal to negative 1. And it's the only one that does not have an imaginary part, and it's the only one, therefore, that doesn't have a conjugate pair. Yeah? Okay, cool. So x6 here is a conjugate pair to x2, so therefore I skipped x5, which is a conjugate pair to the other guy I skipped, which is x3. And then finally x7. Now, we'll demonstrate that x7 and x1 are conjugate pairs, and you can use a similar idea to demonstrate that x2 and x6 are conjugate pairs, and therefore x3 and x5 are conjugate pairs. So what we're saying is if x1 is a plus bi, then x7 would have to be a minus bi, right? So then this is how you realize that. x7 is this, but 13 pi over 7 is the same as negative pi over 7, right? And so then we could replace cosine of 13 pi over 7 by cosine of negative pi over 7, do a similar thing with sine, right? And then you will see that because cosine is an even function, this could be replaced by cosine of just pi over 7, And because sine is an odd function, we know sine of negative x is the same as negative sine x. So then x7 is this guy here, which is exactly the conjugate of x1. And yeah, similarly, you can demonstrate that x2 and x6 are conjugates, or you could just believe my color coding. Alright, so where to from here? We need space. So since we said that we know all 7 zeros, or roots of x to the 7 plus 1, we can do partial fraction decomposition. And here's what the decomposition would look like, right? We'd have to start like this with some unknown constants a1 through a7. But otherwise, these are the linear factors we have, and one for each root. And this here is, in the denominator, x plus 1, right? Because x4 is equal to negative 1, right? Okay, cool. Now, from here, we're going to do this, which is, if you know the partial fraction decomposition process, we have to get a common denominator on the right side of the previous step, right here. And so to get common denominators, what we'd have to do is multiply a1 by all of these linear denominator factors, right? Except for x minus x1. So this a1 here is multiplied by all of the denominators except for x minus x1. And then this a2 here is multiplied by all of the denominators except for x minus x2, and so on. So that's what I showed, which is a1 is multiplied by x minus x sub k for k not equal to 1, and then a2 is multiplied by x minus x sub k for k not equal to 2, and so on. Of course, by the time you're able to write this, you will have had the same denominator on the left and right? And so next we want to know how to solve for a1, a2, and so on. Let's talk about how we solve for a1. So to solve for a1, here in this last equation, on both sides, substitute x1 for x. Notice on the left side, there's no place where we substitute, so we just have what we already have on the left side. But on the right side, when we substitute x1 for x, then in this part, we're going to get a 0. And this part, we're going to get a 0. And everywhere in between, we're going to get a 0. Think about why. Well, I'll help you. We said that this here means x minus x1 times x minus x3 all the way to x minus x7. The only thing left out is x minus x2. So when we substitute x1, we'll have x1 minus x1 as one of the 6 things being multiplied. Well, 7 if you include a2, but the whole thing is 0. And then the whole thing here is 0 and everywhere in between, because there will be an x minus x1 in each of them other than what's multiplying a1, right? So then what we'll have when we substitute x1 for x on both sides of this equation is the following, right? The equation will reduce to this, which is nice because now what we can do next is multiply both sides of this equation by x to the 7th plus 1, and then from there we'll get an equation that helps us solve for a1. Okay, and that's this. So first we clear the denominators and get this, and next to get a1 by itself we have to divide by this guy here. Now notice that this guy here is saying x1 minus x2 times x1 minus x3 times all the way to x1 minus x7, right? But then this here, then, and this a1 is supposed to be an arrow over here, right? It's supposed to say equal a1, not an arrow a1, but I've re-recorded this video so many times you won't believe it, so I'm not going to re-record it here. Just ignore, this is a typo here. It's supposed to be equal to a1, but I already have that on the left side. Anyway, this here I'm saying the expression for a1 can be rewritten as this quotient evaluated for x equals x1. Because this here, x to the 7 plus 1, factors is x minus x1 times x minus x2 times all the way through x minus x7. So if you plug in x equals x1 in there, and then up here, then the x1 minus x1 in the numerator and in the denominator will cancel, and all you'll have is like a 1 in the numerator, and in the denominator you'll have x1 minus x2 times x1 minus x3 all the way to x1 minus x7. but that's the same as what we have here, right? In the denominator. And then, as I said, the numerator will turn into 1 once one of the factors in the denominator cancels with this guy up here. Yeah? Okay, cool. You should be able to see this, but this is one of the few places where this solution is tricky. So if you have more questions, then just leave me comments in the comment section, and yeah, that's that. But you'll get a little bit more help on how we can go from here to here, because a similar thing is going to happen shortly. But again, this arrow and A1, you should ignore. It shouldn't be there. It should just say equal to A1 over here. And so just block this out right here. Pretend like it's not there. Anyway, what's next? Next is this, which is, keep in mind, we just said A1 is this quotient evaluated for x equals x1, right? Okay, cool. Let's get some space. So then, by that logic, in general, a sub k is going to equal this quotient evaluated for x equals x sub k, right? This quotient evaluated for x equals x sub k. But wait, that's saying the same thing as the limit is x goes to x sub k of the quotient, right? Because saying this evaluated at x equals x sub k is saying the same thing as limit is x goes to x sub k of this quotient. And this is actually, like, I think the most inventive part of this solution. Anyway, this limit is clearly of the 0 over 0 form, so we're going to enlist the help of L'Hopital's, which tells us that we can take the limit as x goes to x sub k of the derivative of the numerator divided by the derivative of the denominator. And when we do, we're going to get this for a sub k, and this is just what I said. And then when we actually evaluate this limit, we'll get this. And this is where I said you'd get a little bit more help on that nice, clever trick we did a little bit ago. And let's go back to it. So remember, we'd said that if you want to, you could rewrite this here. Again, ignore that part. This here as this here, right? And so a similar move just took place. And going from here to here. It's a similar idea, yeah? And here, it's immensely helpful, as it was earlier, because now it means that we have x sub k to the 7th in the denominator. Remember, all of the x sub k's, x1 through x7, are such that x sub k to the 7th is going to be -1. And so this in the denominator is just 7 times -1. And so this quotient right here is just going to be negative x sub k divided by 7. And the negative again from the -1 that we would get from this guy right here. Yeah? Okay, cool. So we just figured out more generally what each a sub k is going to be. A1 is going to be negative x1 over 7. A2 is going to be negative x2 over 7, and so on. And in fact, for A4, we know it's going to be negative -1 over 7, which is just 1 over 7. Because remember, A4 would correspond to the root x4, and x4 is -1. That's the one that doesn't have a conjugate pair and is just a purely real. Yeah? Okay, cool. So where to from here? Well, now we figured out A1, A2, all the way through A7. And I've left out a couple of fractions, the same ones involving x sub 3 and x sub 5. Those, remember, are conjugate pairs. But yeah, otherwise, here's what our decomposition would look like, right? And now we're ready to replace A1, A2, and so on with what we know they're all equal to. And so when we do, we're going to be able to, first, let's work on A4 as I've just talked you through it. And because x sub 4 is -1, we know that the fraction involving x sub 4, this guy, is going to simplify very nicely to this. Now, it's the only one, x sub 4, that doesn't have a conjugate pair, and it's the only one that's just a pure real. So we deal with it separately here, and then otherwise we're going to shift these guys so that conjugate fractions, or fractions involving conjugates, are next to each other. I didn't mean conjugate fractions, but you know what I'm saying. Like, so this here is going to be written next to this guy here, and this guy here is going to be written next to this guy, and this guy is kind of the middleman who doesn't have a partner, right? Okay, cool. Trying too hard to be cool. All right, so when we do that, we're gonna get this. Like I said, all I've done is like replaced A1 and A2 and all of them with what we learned that they're equal to, which is gonna involve a -1/7 for all of them, and then an x sub k, right? And then we already dealt with the one involving x sub 4, and it turned out to be this, right? But otherwise, as I said, I've put fractions involving conjugates next to each other, yeah? And then from here, let's set aside this guy, which is simple enough to integrate, because notice that since this is the decomposition of 1/x⁷ plus 1, what we have to do is just integrate each one of these, right? And so we're going to integrate them, and the integral of this is simple enough that we're going to set it aside for now, this fraction. And in fact, the rest of them, other than this guy, we're not going to integrate individually. We're going to take fractions of conjugate pairs together and integrate those two together. So we're going to make one integral out of these two, and then another one out of these two, and a third one out of these two, and then of course a fourth one of this guy by himself. And when we pair them up this way, you'll see that the integral result for these two is going to be very similar to these two, and so on. So that will save us a little bit of time. But yeah, next we do this. And as you see, I've factored out the common -1/7 factor from the 6 fractions, and I've set aside this guy as I said I would. But otherwise, you see this. Now, as I said a little bit ago, we're going to work on just the integral of these two fractions, and we're also going to set aside the -1/7 for now, and then we're going to use what happened here to give us clues on what will happen between these two when we do the integral of these two together, and then the integral of these two together. Okay, so let's go. So when we look at these two fractions, remember we said that if we so chose, we can say x1 is equal to a plus bi, so then x7 will be a minus bi. So these two will turn into these two guys, yeah? And we want to simplify this a little bit more. And so that will look like this. Make space first. That will look like this. And these are pretty straightforward algebra steps, right? You get here, and I think this here is actually identical to what we had, right? Isn't it? Yeah, it's the same as this here, perhaps. Okay, in any case, it has to be. Whether it's written identically or not, it's equal to this, trust me. And then from here, we just got to get common denominators, right? And so I've showed you how to do that here. But I've also done one little thing that's pretty helpful, which is I've distributed this minus sign to the a and to the plus bi here, and to the a and to the minus bi here, and done a slightly different grouping of these three terms, and likewise here, because then we can use difference of squares, one of my favorite things in the world, and see that this denominator, which is now a common denominator to both of these fractions, will work out pretty nicely. Namely, it's going to be this squared plus b. It's going to be this squared plus b squared, right? Okay, and you can check by difference of squares that it will work out that way, yeah? X minus a squared plus b squared. And then the numerator, we have quite a lot of simplifying work to do, but it simplifies pretty nicely. These are all the terms if you like multiplied everything that you need to multiply in the numerator. Like I said, a lot of stuff cancels, and when you cancel everything that cancels, you'll be able to write this, and our denominator is our common denominator here is turned into this, and so same one here, and this here is a simplified version of all this junk. Yeah, now we can do a little bit of factoring here and rewrite it in this way, and once we do, we can reverse the order in which this guy and this guy appear in the numerator, and then split this fraction here into two, and then do an integral of this and then an integral of that. And in doing an integral of this and an integral of that, notice that we're only finishing the integral of the two fractions involving x1 and x7. But yeah, minus the -1/7 that we need to multiply by. If we finish these two integrals, then we will have finished the integrals, the integral involving x1 and x7. Yeah, you already saw how we paired them up and all that good stuff, so I'm not gonna go over that again. All right, I'm repeating myself so that you're following along and I'm not going too fast. Anyway, so let's keep going then. Like I said, what we're gonna do next is find the integral of this and the integral of that. Yeah? Okay, cool. So the first integral is going to be working on this here, right? And you take out a -2, there's a b, and then you want to factor out a b, sorry, there isn't a b, there's a b squared here, and then you want to factor out, but you can see, we want to factor out a b squared from everything in the denominator, but to be able to do that, we must write a b squared underneath this once we factor out the b squared from it, and then we can integrate that b squared underneath this with the x minus a squared in this fashion. And of course, once we factored out a b squared from this guy, we just get a 1. And so, and the -2, by the way, I've written in front of the integral. And so then the b squared in the numerator and the b squared in the denominator we get will cancel. So we just get this, which will have this integral. I'm not going to talk about the details any more than this. Like I said, this video has to end sometime. All right. So then the second integral we said we'd have to work on is this. And here we could take out a 2a, and then we can expand x minus a squared and get this. And then because of what I said earlier, which is all of our roots to this will, the complex ones, and including x equals -1, if we wrote it as a complex number, all of them will have to have norm or magnitude equal to 1. And so remember, we said x1 is a plus bi, but its norm or magnitude is the square root of a squared plus b squared. And we said that the square root of a squared plus b squared, the norm of x1 or the magnitude of x1, will have to equal 1. But if the square root of a squared plus b squared is equal to 1, it means that a squared plus b squared is equal to 1. And so we change this into 1. But otherwise, the rest of my moves are pretty easy to see. And then once we're here, we make a substitution that u be equal to this whole denominator, and then du will be this, from which we get dx is this. And when we substitute for dx and what we called u, then our integral simplifies really nicely. We get this, and this 2 here cancels that 2 there. This x minus a here from a replacement of dx cancels the x minus a in the numerator. And so we just have a integral of du over u with the substitution we make. And so we get a natural log of u plus c, and actually I've abandoned the plus c as you see, because I'm going to need the constant c for something else shortly. But yeah, you know that you write plus c's after indefinite integrals, so that's not worth discussing at length. But yeah, now once we replace u with what it is, we get that this is the integral in full of this guy. And this here is the integral in full of this guy, right? And so if we go a little backwards as a reminder, just a very quick reminder, this here and this here was going to help us find the integral of, they were going to help us find the integral of, I'll just backtrack a little bit because I'm asking too much of your memory. There's so much going on in this. The integral of these two fractions, right? And again, the only thing we've left out is the -1/7. But we just worked out these two fractions, did a lot of simplifying work, right? And then got to, here's the fast forward through the simplifying work we did. And then we got to this place. And then now we took the integral. And then we found that the integrals are going to be this guy at the bottom, and then this guy at the bottom here. So when we add these two, right? When we add these two and then multiply by -1/7, we will have finished with not only the first two fractions, this guy and this guy, but also their full integral, including the -1/7 and all that good stuff. So basically, like, when we paired them, we're done with two of the integrals involving x1 and x7. And so the full answer is going to be this. And notice that if we so wanted, we can simplify this a little bit by distributing this minus sign and changing that to a plus and changing that to a minus and just having a +1/7. So that's what we're going to show in the next step as our solution of the two integrals involving x1 and x7. So that's here. Yeah? And so then we're going to say that x2 is c plus di. I told you I was going to need the constant c. So we're going to say x2 is c plus di. So then x6 is going to be c minus di. and they're gonna work very similarly to how the fractions with x1 and x7 worked out, these guys. And so our final answer is going to be this for this integral here, yeah? And then similarly, our final answer is going to be this for the integral of the two fractions involving x3 and x5. And so if we also remember that we had that middle guy whose integral is going to turn out to be this, then we've got everything we need to finally, Jesus Christ, to finally finish. And so our final answer is going to be this, which is basically the sum of the 3 pairs of integrals we worked on, and then plus this guy. And finally, I wrote a plus k in case you cared about the constant. But this is it, and I might not make another fun, challenging integral video for a while because this took a lot out of me. Like, I basically had to give up all of my Sunday to do this because I kept on recording and re-recording it just to make it right. And I hope that you see all the effort that went into it and you appreciate it, and yeah, share this video. Yeah? Okay, cool. All right. Take care and keep watching.